for joining in this Friday afternoon, or for JJ Friday morning, I guess, seminar. So allow me to introduce our speaker. So John, or JJ Zanazzi, he received his undergraduate degree from the University of Northern Arizona in 2013, if I'm not mistaken. And he's not only a degree in that in physics and astronomy, but he combined it with a degree in mathematics as well. So he then went on to do a PhD in Cornell University under the supervision of Danlai. And he defended his thesis not that long ago in 2018. So he's a young postdoc. And he currently works as a postdoc at the University of Toronto at the Canadian Institute for Theoretical Astrophysics. And John is interested in the theoretical aspects of all things dynamical, as he says himself, ranging from protoplanetary disks and exoplanets all the way up to neutron stars and black holes. So, John, please, you have the floor.
Okay. Yeah. Thank you very much for the generous introduction. Yeah. So, hold on a second. About to share my screen. Can everyone see the screen that I'm presenting?
Yes.
Okay. Excellent. Hold on one second. All right. So it's everything's working well, or okay. Everything looking good, or all right.
Looks very good. Yeah.
Excellent. Okay, so thank you again, Connie, for inviting me to give a talk at your seminar. So as I've been generously introduced, my name is JJ Zanazzi. I'm a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics. And at CETA, the person I work primarily with is Professor Yenxin Wu, who's affiliated with the University of Toronto. And what we were talking about today is work that we did together looking at how effectively this new dissipation mechanism called resonance locking works to circularize entire populations of binary stars. So this is really nice work that I'm really happy to be able to present here. But before I go into the work which I went ahead and did, what I want to do briefly is go over the motivation behind why we decided to take a look at a very old problem to figure out why stars go ahead and circularize their orbits. And so shown here is a little cartoon for the setup that we're going to be considering this entire talk, where at the center of the system, we have a host star, which is dissipative. And orbiting this host star is a centric binary companion with an eccentricity E and an orbital period P orbit. And because the companion exerts a periodic tidal forcing on the host, this periodic tidal forcing drives dissipation within the host, which works to exchange energy and orbital angular momentum with respect to the companion. And because the host is dissipative, this dissipation process, whatever it is, works to slowly decrease the eccentricity of the companion with time. And the main way different tidal theories differentiate themselves from one another is they predict different predictions for the process under which this dissipation actually goes ahead and takes place. And before I talk about the different theories to figure out how this dissipation works to circularize the orbits of eccentric binary stars, what I'm going to go over is the ways which you go ahead and test these different tidal theories, or at least the ways that are available at the current moment to test these different tidal theories. And the main way you do it is you look at stellar clusters, because the advantage of stellar clusters is that all the stars or binaries within the stellar cluster are expected to have more or less the same age. And when you're able to look at a population of stellar clusters, one way in which you can figure out how efficient tidal dissipation is happening in these systems is you look for a quantity which known as the circularization period. And the circularization period is supposed to be defined in a way such that when you have an orbital period of a binary less than the circularization period, all of the binaries in this class of objects have nearly circular orbits. Well, when the orbital period of the binary has an orbital period greater than the circularization period, you can still have circular binaries, but this class contains all of the moderately and highly eccentric binaries. And the first person to actually go ahead and come up with a rigorous measure for what a circularization period is Meebo and Matthew in 2005. And what they did is they ran a whole bunch of simulations based off of Zahn's tidal theory, and found that this damped exponential function with this cutoff period at a certain critical period known as P prime, when this damped exponential function fit the simulated binary population well. So because it fit the theoretical populations for how Zahn's tidal theories are expected to circularize eccentric binary stars, he then went ahead and fit this function to a whole bunch of binary star populations. And he defined what the circularization period was by where this fitting function had a value of about 1%. And here is his main result, which caused a bit of a stir the community in the 2000s, where on the y-axis, we're plotting the age of the different stellar binaries clusters, which he looked at. While on the y-axis, we've plotted the circularization period, which he measured for these different binary stars. And you can see when the binaries have ages less than about a gigayear, all of the binaries have circularization periods around 8 days. But when the age of the binary exceeds about a gigayear, the circularization period slowly increases to a circularization period of around 15 days. And the reason why this was so stirring to the community is none of the tidal theories which had been developed to date could explain this correlation. So in the thin gray line and the dotted gray line, we are showing the predictions of main sequence equilibrium tides, which is a theory developed by Zahn, along with resonance locking, which I'm going to be talking in a lot more detail in a bit, but was primarily developed by John Papalouzeau, Witt, and Safavier in the 80s to 2000s. And these two tidal theories predicted the circularization period should slowly increase with the age of the binary. While the other main tidal theory people were considering at the time was circularization driven primarily during the pre-main sequence, which was a different theory, which was also developed by Zahn, which argued that stars are the most dissipative during the pre-main sequence evolution. And as a result, the pre-main sequence evolution should drive dissipation of stellar binaries out to 8 days. And this predicts that the circularization period should be roughly independent of age. And so this particular observational result couldn't explain the data at the time. And for a while now, this has been considered an outstanding problem in figuring out why stellar binaries go ahead and circularize orbits out to the orbital periods which they're observed to. And because this was a long outstanding problem, what Jensen and I decided to take a closer look at was this new tidal theory, which has been proposed in the past decade or two, known as resonance locking. And what resonance locking argues is that resonances are primarily driven, or that's the main way in which binaries circularize their orbits are due to near resonances with the harmonic of the orbital frequency and a natural oscillation frequency of the host star. And these resonances, which drive a ton of dissipation, are sustained as the host star evolves eternally, causing the natural oscillation frequencies to also move. And so this theory was originally developed by John Papalouzeau and Witt and Safavier like a few decades ago, but it's really been popularized within the past 10 years by Elliot Quartet's graduate student Burkhardt in a series of papers along with Jim Fuller, who's a professor at Caltech. And these authors have argued that this new tidal theory can potentially explain why Saturn's moons migrate outwards at the rates which they're observed to, along with these things called heartbeat stars, which are these highly eccentric binary stars with light curves which undergo drastic variations, which also often exhibits pulsations which are located at harmonics of the orbital frequency of the companion. And what Jensen and I decided to do for our work is to look at how effectively this new tidal theory can circularize binary star populations to see if this new tidal theory can explain the observational results, which I discussed previously, which has been a real trouble to explain for quite some time. And so what I'm going to talk about first is the theoretical kind of underpinnings to the work which Jensen and I did, And I'm later going to talk about how this theory goes ahead and compares with observations in a great amount of detail. But first, I'm going to talk about the theoretical background behind the idea and the primary theoretical results which Jensen and I found. And so before I talk about the theory which Jensen and I went ahead and did, I'm going to review the physics of how dynamical tides actually go ahead and work in stellar binaries. And so the way dynamical tides work is instead of assuming that you have an equilibrium tidal bulge, which solely lags behind the location of perturber, which drives dissipation due to the small phase lag of the perturber's bulge of the host star's bulge with respect to the perturber. The way you calculate dissipation in dynamical tidal theories is you self-consistently figure out how the perturber excites all of the natural oscillation frequencies within the host star. And the dissipation, and to calculate the dissipation between the perturber and the host fluid body, what you do is you sum over every single one of the natural oscillation frequencies, which is excited by the perturber, to calculate how an orbital angular momentum is exchanged between the spin of the host star and the perturber, as well as energy is exchanged between the host star and the orbit. Because dynamical tides, a crucial ingredient in dynamical tides are the natural oscillation frequencies in the host. What I'm going to talk about a little bit are the primary natural oscillation frequencies, which I'm considering in this, which Jensen and I considered in this work, which are gravity waves. And these are natural oscillations whose primary restoring force are buoyancy forces. And so I'm sure a lot of members of the group I'm talking about here are very familiar with gravity waves, but I'm just going to give a very brief overview for how they work, because it's going to be really important later on. So these tidal oscillations are low frequency oscillations which have frequencies which are roughly less than the dynamical frequency of the host star or the Brunt-Weisshauer frequency of the host star. If you look at the radial wave number to the second power, this radial wave number is proportional to the square of the Brunt-Weisshauer frequency, which tells you roughly how stratified your body is. And because the square of the radial wave number is positive when the Brunt-Weisshauer frequency is positive, gravity modes primarily propagate in radiative regions of stars, while they're evanescent in convective regions of stars, where the Brunt-Weisshauer frequency is negative. And shown in the panel to the right here, we have the horizontal displacement of a G-mode as it propagates across the host star. And as you can see, what we are displaying with the solid red curve when the Brunt-Weisshauer frequency is positive. And when the Brunt-Weisshauer frequency is positive, the tangential displacement of the G-mode is highly oscillatory and propagates across the radial extents of the star. While when the Brunt-Weisshauer frequency is negative, the tidal displacement is evanescent, and it slowly damps its amplitude in convective regions. So to figure out how G-mode oscillation frequencies evolve, the main thing which you have to look at is how the radiative regions of stars evolve over their pre-main sequence and main sequence lifetimes. And so by using MESA codes, Jensen and I took a really detailed look at how you'd expect stratification to evolve during the evolution of solar type stars. And it turns out the time under which the radiative zone undergoes the most evolution is during the honey track, during the pre-main sequence evolution of the host star. So during this phase, the luminosity of the star is constant, and the star is still heated by gravitational contraction. So it's still undergoing Kelvin-Helmholtz contraction as it evolves along the pre-main sequence. But when the Henny track starts kicking in, this happens when the core temperature increases to a level such that the opacity within the core drops, which causes the regions within the core to ionize, and this causes the opacity to also drop because it becomes dominated by free electron scattering. And when this all happens, what happens to the core is the core becomes radiative, and it slowly expands the region under which the star transports its energy primarily through radiative diffusion rather than turbulent convection. And the result is when you look at how G-mode oscillation frequencies evolve during the host star's internal evolution, they evolve the most by far during this Henny track because of the dramatic expansion of the region in which they propagate during the Henny track. And in addition to figuring out how the natural oscillation frequencies evolve, another important ingredient for figuring out how the star dissipates energy is looking at the damping rates of Gmodes. And it turns out the two dominant mechanisms which dissipate the energy of a Gmode is radiative diffusion and turbulent convection. And so I'm not going to describe in a whole lot of depth how these processes work to damp the amplitude of gravity modes. But the key takeaway is if you just look at the y-axes of the two graphs, where on the top we're plotting the damping rate from radiative diffusion. On the bottom, we're plotting the damping rate from turbulent convection. The values for the rate of diffusion over a range of G-mode oscillation frequencies, which is denoted by F here, is significantly higher than that for turbulent convection. So as a result, the gravity modes which we're considering in this work are primarily dominated by radiative diffusion rather than turbulent convection. Okay, so this what I just discussed are the condition or how these gravity modes go ahead and damp their energies along with evolve during the pre-main sequence and main sequence evolution. Now what I'm going to talk about is the conditions which you need to satisfy in order to stably lock onto a resonance of the host star to circularize your orbits through this resonance locking process. So what I'm plotting in the cartoon to the right here in the thick red curve is the orbital evolution timescale. So this quantity tells you how quickly the orbit evolves under the action of tidal dissipation. And the lower this quantity is, the faster your orbit is going to move inwards due to energy dissipation from resonance locking. And so if there's no internal evolution going on within the host star at all, if you're really, really close to exact resonance between an orbital harmonic and a natural oscillation frequency within the host star, which we're denoting by sigma here, when you're really, really close to one of these resonances, you get a really big dip in the orbital evolution time due to these resonances, because you have a big increase in the amount of dissipation due to these resonances. And if nothing else is going on, what happens is when you're really deep into one of these resonances, you're very quickly pushed out of resonance due to the big increase in tidal dissipation. And as a result, early authors, in particular Turcoing in 1998, along with John Papalouzeau and a number of other authors, argued that these resonances didn't play a huge role in the orbital evolution of solar mass stars. But one thing they didn't include in their calculations is how the evolution of the natural oscillation frequencies themselves also affects the circularization of binary stars. So if in addition to the orbital evolution, you have the natural oscillation frequencies themselves evolving as well, when the binary is pushed inward, the location of the G mode can slowly catch up to the location of the binary, working to increasingly push the binary to shorter semi-major axes or smaller orbital periods. And when the evolution time is longer than the minimum of the orbital evolution time right at resonance, there's a stable location which the binary can lie at to stably lock onto a given resonance and slowly be driven inward by the slow evolution of the host star. And when you have a mode evolution time which is shorter than the orbital evolution time right at minimum, which we're going to note by t-orbit min throughout this talk, what happens instead of the binary stably locking onto a resonance, the resonance just goes ahead and sweeps by the binary. So the key condition to figure out if a binary can stably or unstably lock onto a resonance is to figure out if the mode evolution time is longer than the orbital evolution time at the minimum at the peak of this resonance. And that's the primary calculation which we consider in this work. And that's the primary calculation which Jensen and I went ahead and did to figure out how efficiently these binaries evolve. So what I just described is how you can figure out how the semi-major axis of the binary evolves. And so in particular, the key condition for the resonance locking to actually go ahead and take place is the mode evolution time stays closely locked to a natural oscillation frequency in the host star. And when you set these two quantities equal to one another, you can calculate how the semi-major axis of the binary just goes ahead and evolves as the natural oscillation frequency of the host star slowly increases. And in addition to that, you also have to figure out how orbital angular momentum is exchanged between the host and the companion. And with this, you can figure out how the eccentricity of the binary evolves. And due to technical reasons, which I'm not going to discuss in this talk, it turns out that the modes which are by far able to drive the most amount of circularization in stellar binary populations are zonal modes, which have no angular momentum. So they're axis symmetric modes, and as a result, they have no angular momentum. And because they have no angular momentum, they can't exchange orbital angular momentum with respect to the binary companion, which implies that when you have resonance locking driven by zonal mode, the orbital angular momentum of the binary companion stays constant throughout the entire process. So once you figure out how the semi-major axis moves in, all you have to do to figure out how the circularization, how the eccentricity decreases, is to just calculate the new eccentricity along the track of constant orbital angular momentum. So this makes the calculation of figuring out how the binary circularizes its orbit actually quite simple. The main thing you have to figure out is how long the binary is driven onto a stable resonance lock. So this is the primary theory for the calculations which Jensen and I went ahead and did. What I'm going to discuss now are the results from these calculations, figuring out how efficiently this resonance locking process can circularize eccentric binary star populations. And so what I'm showing here are a number of different oscillation periods for gravity modes during the pre-main sequence to the left of the black dashed curve, and during the main sequence evolution to the right of the black dashed curve for a solar mass star. And what the colors denote is when you have a moderately eccentric orbital binary with an orbital period equal to the whatever gravity mode oscillation period you're considering. And the red curve denotes regions in the parameter space where this moderately eccentric binary is unstable to resonance locking because the orbital evolution time at minimum is longer than the mode evolution time. Well, the blue curves denote where you are stable to resonance locking, where the where T orbit min is shorter than the mode evolution time. And as you can see, because the region and parameter space which you can drive stable resonance locking is much more extended than the region of parameter space where you drive unstable resonance locking. When you compare the curves to the left-hand side of the black dash curve to the right-hand side of the black dashed curve, you expect the pre-main sequence in comparison to the main sequence to drive much more stable resonance locking. And an additional reason where the pre-main sequence drives much more resonance locking than the main sequence is the oscillation frequencies themselves evolve much more during the pre-main sequence than the main sequence. And that has to do with the fact that the primary reason you get these drastic evolutions is due to the slow evolution of the radiative zone of the host star during the Henry track. Okay, so before we do any calculations, we already expect that the pre-main sequence should drive much more circularization than the main sequence. And what I'm showing here is actually the time evolution snapshots of the binary orbit themselves, which are locked onto stable resonances and have their orbits circularized. So the solid curves on the top panel display the orbital periods of a number of different eccentric binaries, while the solid curves on the bottom panel show the eccentricities of a number of different binaries which we're considering, which are circularized by this resonance locking process. And the crosses and the diamonds on the top-hand panel show the a harmonic of the Gmode oscillation period, which the binary stably locks onto resonances during some part in its evolution. And you could see when you have a stable resonance lock, so when the orbital period encounters a resonance such that it can undergo resonance locking stably, this process works to slowly decrease the binary orbital period for a significant amount of time until at some point the eccentricity decreases to a level where the T orbit min is actually longer than the mode evolution time. And so the reason why at one point the T orbit min is shorter and then later on it's longer is the orbital evolution time at minimum depends sensitively, in addition to the mode properties, it also depends on the binary eccentricity. And when the orbital evolution time at minimum is longer than the mode evolution time, you suddenly break your resonance and you leave the binary stranded sometimes at a moderately eccentric orbit at a short orbital period. This is, I'd like to mention in terms of how the binary actually goes ahead and evolves. This is very different from most other conventional tidal theories, which predicts that as that the circularization process is kind of this continuous process where you never really stop circularizing at a certain time. So resonance locking, in comparison to other tidal theories, predicts that at some point the binary just is kind of left stranded at some particular point in its evolution due to this breaking of the resonance. Okay, so that's the time integrations of how particular orbits go ahead and evolve. What we're displaying here is an example calculation for how an eccentric binary population goes ahead and circularizes its orbits due to resonance locking. And so what we're plotting here in the thick magenta plot points are the final eccentricities and orbital periods of a very simple startup eccentric binary population, while the thin cyan lines show the tracks over which these binaries undergo circularization. So the start of the line is where they start off, and they circularize to their final magenta points, which are displayed in this diagram. And the cyan lines denote the circularization which occurs during the pre-main sequence, while the magenta lines show that when the circularization happens during the main sequence. And as you can see in this figure, there are very little points which have magenta lines for a significant region of the parameter space, which means that the primary time in which these binaries circularize their orbits is during the pre-main sequence. And in comparison, the circularization you get during the main sequence is more or less negligible. And I'm not going to display these additional circularization tracks when you change the host star mass, but the circularization process more or less is independent of the host star mass, at least for stars around the mass of a solar mass. And the reason why is the Henny track for moderately massive stars up to 2 solar masses is more or less independent of the mass of the host star. The stellar structure is very similar, and as a result of the similar stellar structures, during the Henny track, you predict similar circularization periods for this resonance locking process. And all of these binaries have, due to resonance locking, when they have masses around the solar mass, circularize their orbits out to 4 days, out to orbital periods of 4 days. Okay, so what I just discussed are calculations which assume that the damping rates of these modes is totally linear. And it turns out there's a really, really big caveat, which we didn't consider originally in our work, but the referee pointed out. And we looked into a lot more detail in our revisions, which we just submitted, which is that nonlinearity of these modes is really, really important, most likely. And so the reason why nonlinearity we need to consider is in order for resonance locking to actually take place, the G mode has to get excited at one end of the star, and it slowly grows as it bounces back and forth between the stellar core and the edge of the star. And this slow growth process of as the G mode is bouncing back and forth works to, you need this G mode to bounce back and forth from the core to the star in order to grow the mode amplitudes to the linear amplitudes which cause the most dissipation during resonance locking. However, it turns out that these modes can often become nonlinear, especially during the pre-main sequence. And the main consequence of this nonlinearity is when the mode amplitude grows to a sufficiently large value. Instead of bouncing back and forth at the stellar core, what happens is the mode suddenly damps its amplitude very, very rapidly and is not able to continue bouncing back and forth between the surface of the star and the core of the star. And Yanshin and I went ahead and estimated this nonlinearity parameter, which tells you roughly how large the first derivative of the radial displacement is. And when this nonlinearity parameter is greater than 1, you expect this overturning to actually go ahead and occur. And we estimated it, clearly when we estimated at the center of the star at a orbital period of 1 day, the nonlinearity parameter had a value of around 10,000. And so nonlinearity is almost certainly really important for these different stars. And Yanshin and I went ahead and we calculated rough estimates for how we expect this nonlinear process to affect the circularization periods which we calculated assuming just the mode amplitudes are totally linear. And we argue that it should reduce the circularization periods by around 35%, this nonlinear saturation process. But our estimates are based off of a lot of uncertain physics that are going to require a little bit of future work. And in particular, I'm planning on doing hydrodynamical simulations of this process to figure out how efficiently it will damp energies when you're driven, when these standing modes get excited to nonlinear values. Okay, so that's a really big caveat for the rest of the talk. We're just going to assume that the linear process works fine and dandy, and figure out how the linear calculations of resonance locking compare with observations. Okay, so what I'm plotting here is the first comparison which we did, which was just a very, very simple chi by eye to figure out with the new binary data, which we now have a much greater sample of eccentric binary measurements at short orbital periods, how the new binary compares with theoretical predictions of resonance locking. So shown in this diagram here with the blue points are the measurements of eclipsing binary eccentricities, while the green points show spectroscopic binary eccentricity measurements. And the dashed black curve shows the theoretical prediction with no free parameters. The only free parameter is MESA. What the first principles theoretical predictions for resonance locking predicts for the circularization of eccentric binary star populations. And with a quick chi by eye, the first principle predictions for resonance locking agree with the binary data really, really well. So Yenshin and I decided to look in a lot greater detail to figure out quantitatively how well these new binary data compare with observations with the theoretical predictions from resonance locking. And so this is work that Yenshin and I are still doing. The primary results, which I'll be presenting today, are not going to be modified drastically by the calculations we're undergoing right now, however. So the main thing we're doing right now is we're trying to make sure that we have calculated the error bars correctly for all the different eccentricity measurements, which we're using to constrain these tidal theories. But the main results, which I'll be presenting, should not be changed drastically. Okay, so one of the main things when you look at a lot of new studies for how you expect binary stars to circularize their orbits, and you compare this with the actual observed spectroscopic and eclipsing binary star populations, is all these studies seem to find kind of two populations of eccentric binaries. So what I'm displaying here is a new result by Amory Trio in 2017, but if you look at other surveys like Adrian Price-Whelan and Windemuth et al., which I'll be discussing also, you get very similar looking figures where when you look at the data, just looking at it by eye, there seems to be a nearly circular population out to orbital periods of around 10 days. On top of this nearly circular, this overdensity of nearly circular orbits, which is the majority of binary, there is also a small population of highly eccentric binaries, which have much higher eccentricity orbits at short orbital periods. And the reason why this is very, very puzzling is if you look at the internal structures of these stars, which are plotted here, there isn't really any big difference in the internal structures of the stars. So if you use first principle tidal theories to figure out how these orbits should go ahead and circularize, they should all have very similar orbital periods. You shouldn't have this kind of dichotomy in different eccentric binary star populations. And so the hypothesis, which Yenshin and I went ahead and tested, is are there actually multiple populations within these new eccentricity measurements which people are getting, with only one population circularized by tides. So only the highly eccentric binary star population is circularized by tides, and the nearly circular population out to orbital periods of 10 days gets its nearly circular orbits by some other process which might not be due to tides, maybe disk migration. And so before I talk about the methods which we go ahead and use to constrain multiple binary populations, I'm going to very briefly go over how eccentricities are measured in different types of binaries. So the main way in which people have measured the eccentricities of binaries for a very long time is through spectroscopic binary measurements. So when you look at the spectral lines of stars, and the star is in an eccentric orbit, the spectral lines of apoaps are redshifted. As the binary goes around its orbits, the spectral lines undergo redshifting and blue shifting. And once you figure out how the anomaly in the radial velocity evolves over a single orbit of the binary, you can use this radial velocity to calculate or to estimate the eccentricity of the binary. And so when you go ahead and you fit a Keplerian orbit to this radial velocity curve, you have a most likely eccentricity measurement, which we're going to know by EI. And this eccentricity measurement has an uncertainty, which is affected by the observation errors, which we're going to know by sigma. And the actual eccentricity of the binary is given by a Gaussian probability distribution with a standard with an uncertainty which is constraint, which is given by the observational errors. And the main sample, which we go ahead and use to constrain the orbits of binaries with spectroscopic binaries, is the results from the Apogee survey, which was compiled by Adrian Weiss-Price-Whelan recently in 2020. In addition to spectroscopic binaries, we also look at eclipsing binary data. And so these binaries constrain the eccentricities much more poorly because instead of being able to get a constraint on the actual eccentricity, you're only able to get a constraint on the projected eccentricity in the direction on the observer's reference plane on the plane of the sky. And the reason why is the way you measure the eccentricity is you use the fact that during periaps of an eccentric orbit, the binary is moving much quicker than apoaps. And by figuring out the difference between the times of primary and secondary eclipses of the eccentric binary star, you can estimate the projected eccentricity of the binary. And given this estimate of the projected eccentricity of the binary, you can figure out the probability distribution of the true eccentricity of the binary by assuming that the longitude of the ascending nodes have a uniform distribution between 0 and 2 pi. And the sample of binaries which Yanshin and I use to go ahead and constrain the eccentricity distributions using eclipsing binary data are the eclipsing binaries recently analyzed by the Windemuth et al. Survey looking at the Kepler binaries, which was done in 2019. Okay, so these are the different types of binaries which we use to constrain the populations. Now what I'm going to discuss are the methods which we use to tease out multiple populations of binaries. And so what I'm showing here is a simple cartoon of the binned probability distribution after you sum the different individual probability distributions of all the different individual binary measurements. And this is more or less a cartoon of what every single binned probability distribution looks like at short rotor periods. So if you look at the probability distribution at small eccentricities, there's a really big peak in the probability distribution, which is due to the fact that most binaries at short orbital periods have nearly circular orbits. But in addition to this really big peak, there's this long extended tail, which extends to much higher eccentricities at short orbital periods, which if the nearly circular orbit binaries were only described by tidal dissipation, would not exist. So the way in which we constrain the median eccentricities of binaries at short orbital periods, which tells you how the eccentricities of most binaries go ahead and behave as you change the orbital period. We calculate where the cumulative probability distribution of the binned probability distributions has a value of around 0.5, which gives you where the median eccentricity goes ahead and lies. And we define what we call the envelope eccentricity, which we're going to argue is the eccentricity which describes how tidal circulation circularizes binary star populations by where the cumulative probability distribution of the short period binaries have a value of around 0.9. And so what we're going to argue is that the median eccentricity better describes short binaries which have their orbits formed by some other process other than tidal circulation, while the envelope eccentricity is a better measure for how tidal circularization affects the binary eccentricities at short orbital periods. Shown here are the results of one of our primary calculations done in our work, which is upcoming. Where in the black dots, we have displayed our estimates of the envelope eccentricities at short orbital periods. And the error bars are just calculated using standard bootstrapping analyses. And in comparison, the average eccentricity, the median eccentricity, which measures the eccentricity most binaries have, are shown in the brown curve. And so you can clearly see that these two distributions are very, very, very different from one another and have very different circularization periods, which likely means that they form from two very different processes, where some other process leads to most binaries having low eccentricities at short orbital periods. And if you compare the first principle predictions from resonance locking, which is shown in the thick cyan curve here, with the data, the constraints on the envelope eccentricity, the match between theory and the envelope eccentricity constrained with data is actually exquisite. So the constraints on the envelope eccentricities at short orbital periods agree really, really well with the theoretical predictions from resonance locking. What we displayed here are results for G-type primary stars, so solar mass stars. And we find that the envelope eccentricity has a circularization period of around 4 days, while the average eccentricity has a circularization around 10 days. And when you look at different spectral types of the star and you compare it with the first principle predictions of resonance locking, the data agree with the first principle predictions of resonance locking within around 2 sigma for every single data point, which is considered, which is pretty remarkable, considering how hard it was to get tidal theories to agree with the data for so long. Okay, and also the average eccentricity, which gives you the most likely this value which most binaries have circular orbits out to is around 10 days. And when we also looked at how the age of the binary goes ahead and affects these two different distributions, so it's much harder to tease out how the age of the binary affects these, because there's very small sample sizes of young binaries which have ages less than 100 million years. And there's and the ways in which you date stars using evolved binaries, there aren't a whole lot of age measurements to figure out how evolved binaries behave at short orbital periods. What we used in our studies, we used the age estimates for the eclipsing binary stars and the Windemuth et al. Survey. So we do find a tentative increase in the circularization period with age, but because the data which we're using to constrain these two populations is so sparse for both populations, we can't make any very firm conclusions for this point. Okay, but the key takeaway here, though, is if this is true, if there is a tentative increase in the circularization period with the age of the binary, what this implies is that resonance locking might not be the entire story. There might be an additional process which works to circularize the eccentric binary star population. Okay, so in addition, we also looked at the if you have both a primary and secondary star which lie either below or above the Kraft break. So previous works have argued that stars above the Kraft break have shorter circulation periods than stars below the Kraft break, because the stellar structures of main sequence stars differs very drastically below and above the Kraft break. And we looked at the new data of binary eccentricity measurements which are below and above the Kraft break. And we actually don't find, with these new binary eccentricity measurements, the trend that has been reported previously. And in fact, we actually find a slow increase in the circulation period. But this, again, this is a very tentative result, because as you can see, the number of hot binaries which we're using to constrain these populations is very sparse. Okay, so at the moment, the data and the predictions of resonance locking in comparison with the data is very encouraging. But we still have this problem in that the results of Meebo and Matthew in 2005 predicted very different things for how resonance locking should go ahead and circularize binary star populations. So what we argue in our new work, Jensen and I, is the reason that this prediction is not true. Oh, sorry. So it's 9:45. How much longer do I have to give my talk? It looks like I'm running out of time. Is it okay if I'll take like an extra 5 minutes to wrap everything up? But
sure.
Okay.
Yeah, sure. It's okay.
Okay. All right. Yeah. So I'm almost done. So what Jensen and I did to figure out why Meebo and Matthew's results gave very different results than the current data is we argue there are two reasons why this old method gave weird results. And it's first due to the small sample sizes with which Meebo and Matthew were using to constrain binary star how binary stars behave at short orbital periods. And second, the methods which they went ahead and used were not sensitive to multiple populations of eccentric binaries at short orbital periods. And so to show that you can get a spurious result with a small number of binaries with two populations, what we did is we constructed a really simple toy model, which at short when you have an orbital period less than about 10 days, you are most likely to have a nearly circular orbit. So an eccentricity of 0, but you have a 30% chance of having an eccentricity anywhere between 0 and the top of this dotted black line. While when you have an orbital period longer than about 10 days, you have roughly a uniform probability of having eccentricity anywhere between 0 and the top of this dotted black line. And using this very simple toy model, what I'm displaying here on the bottom 3 panels are examples of the different binary star populations which you get after you draw synthetic binaries out of this population. And on the top panel, we have displayed one of the populations which Miwo and Matthew in the original study originally constrained to calculate the short orbital periods of the young binary star population. As you can see, with the same population, it's really easy to get very drastically different circularization periods after drawing binaries from this population, just due to the fact that you have a small number of binaries which are drawn out of multiple distributions. And when we go ahead and we calculate the actual distribution which you get from the synthetic binary star population, which I'm plotting here are the binned synthetic circularization period values for this single binary star population. The black dotted points show the probability distribution, which is binned at different circularization periods, while the vertical green lines on top show the Miwo and Matthew circularization period measurements, which were reported in their original work. And so you can see that the median eccentricity from this very simple binary star population, which we considered in our work, has a very large uncertainty. So the 1 sigma uncertainties are around plus or minus 3 to 4 days, while the 2 sigma uncertainties are much, much larger. And when you compare the median eccentricity and its uncertainties, most of the original circularization periods which Miwo and Matthew originally measured lie within 1 sigma of this median eccentricity of this simple binary star population, which we constructed with our toy model. And every single one of the binary star circularization periods which were recorded in Miwo and Matthew are within 2 sigma of this median eccentricity. And so what we argue is that the reason why Miwo and Matthew got the spurious results is he was considering a small number of binaries which actually have multiple distributions. And so here are the primary conclusions of our work, which we went ahead and did. So resonance locking circularizes primary binaries out to around 4 days, which is more or less independent of the mass of the host star. And this resonance locking process happens primarily during the pre-main sequence, and the additional amount of circularization which occurs during the main sequence is negligible in comparison. When comparing this prediction to data, the highly eccentric binary population which circularizes down to 4 days is consistent with the binary data, while there's this additional nearly circular population of binaries which circularizes out to 10 days. It's not really clear what causes this, but one potential explanation is formation due to disk migration. The predictions, the first principle predictions of resonance locking hold when you change the spectral type of the primary, the binary age, and effective temperature. Although this conclusion is still tentative, Jensen and I are still doing work to figure out if this is actually true. And the results which Miwo and Matthew originally came up with can be explained, that the fact that he got such longer circularization periods can be explained by the small number of statistics of that work due to 2 populations generating the circularization periods which he measured. Thank you very much for coming to my talk, and I'm happy to take questions if you have them.
Thank you, JJ. Very interesting talk. Thank you.
Yeah, thank you. Yeah.
So, okay, so let's take questions. So if you have a question, please mention it in the chat and I will call out your name, and as usual, I will give priority to the younger people if there are multiple persons. So the first one is Tomer.
Hi, there's a lot of sun here. Thanks a lot for the talk. I was wondering relatively in the beginning actually about the observations. I'm not from the field. I was wondering whether, well, generally whether, since you're looking at, into stars in clusters, whether dynamical interactions or interactions with triple bodies can also impact this interpretation, and whether that's accounted for.
Yeah, that's an excellent question. So we also, so with the eclipsing binary star measurements, one way of figuring out if there is a possible tertiary companion is to figure out if there's transit timing or eclipse timing variations within the eccentric binary star. And this was actually done in Windemuth's study. And with this, you're able to actually compare the stars which might have triples to the stars which are most likely don't have triples. And when you do this comparison, you do not find a significant difference between the stars which likely have companions and the stars that don't have companions. So it does seem like the existence of a triple or not does not seem to significantly affect the binary eccentricity distribution measurement constraints which we report in our work.
Okay, thanks.
No problem.
Okay, any other question? Maybe, okay. Connie mentioned that she's old. Then there is Cole, who is also old, but Seaman is young. Seaman.
Okay, hi JJ, thanks for a nice talk. You're talking mostly about stars with a convective envelope and a radiative core. Are you planning to do anything with stars that are born with a convective core, or how would this tidal evolution change, basically?
Yeah, no, that's a really good question. So if you have a convective core, so what happens as the Gmodes propagate inward, their amplitudes get largest near the core due to the fact that due to the stratification and density structure there. And so if you have a convective core, especially a small convective core, you don't get the crazy nonlinearity. So the calculations are actually much better and much more reliable if you have a convective core. Yeah, so you're absolutely right. High mass stars, especially during the main sequence, have these convective cores. But they also don't drive nearly as much stable resonance locking because you really need a convective envelope to kind of have this lever for the eccentric binary to kind of lock onto one of these resonances. Yeah, so when you have a convective core, if you have just a high mass star in the main sequence, you drive not nearly as efficient resonance locking. But if you have a pre-main sequence star, which has a convective core and envelope, then you can drive stable resonance locking much more effectively. And so I might also be investigating if you can create a convective core due to the nonlinear dissipation mechanisms which I'm discussing today. So that's very, very future work potentially, but that is one thing that I'm considering investigating. But that's an excellent question.
Very interesting, thank you.
Yeah, thank you.
Okay, maybe I will let Connie ask her first, her question first, because she has to leave at 4 o'clock. So Connie, please.
Well, actually, Seaman asked it, and I'm happy with the answer, so I can only give a comment. Please do the computations for OB stars. We are very interested in that.
Yeah. No, yeah. So, yeah, and in particular, I didn't mention OB stars at all, but OB stars are really interesting as well because they, so the data isn't nearly as constraining as lower mass stars just because there's less OB stars, but they're much more centric at short orbital periods, which implies that resonance locking, for whatever reason, doesn't seem to happen for OB stars. And one potential explanation, which Yenshin and I are thinking about, is the reason why it doesn't take place is the pre-main sequence for OB stars is super short compared to lower mass stars. And that means that resonance locking just doesn't have time to take place.
Yeah, that's why it's so interesting for us. But anyway, now it's younger people's time.
Okay, yeah, thank you very much for the question, Connie.
Okay, cool.
Well, I'd like to first thank Joris for being called old. And then thank you for that very interesting talk. There's a lot to think about there. But the question I would like to ask is focusing on binaries where the eccentricity is changing due to mass transfer. Do you think that the structural changes, which would then accompany the mass transfer, could like propagate into this mechanism where you kind of like drive towards a resonance really rapidly? Do you think that has any contribution to that process at all?
Oh yeah, mass transfer is definitely going to affect how this happens. So in addition to just to modifying the structure of the star itself, which you just mentioned, right? So during the pre-main sequence, how the structure evolves depends very sensitively on accretion because it's heated by gravitational contraction. There's also the fact that mass transfer itself will also modify the orbits of the binaries. And so it's, I know Katie Breverick, who used to be here also at CETA, has thought really carefully about how mass transfer affects the orbits of the binaries. And that's still also widely open. And people are still very uncertain about how the mass transfer process itself goes ahead and changes the orbits of the binary. So at the moment, my answer is that's an excellent question, which I don't have a good answer for.
Well, yeah. I have a very particular type of object in mind. It's there's subdwarf B stars that are in long eccentric orbits with lower mass main sequence companions. And there's been a lot of work done in our institute as well, trying to explain this as phase dependent, like mass transfer that pumps the eccentricity.
Okay.
But I do think that, just thinking out loud, I would be very interested to see how your resonance locking kind of builds into that, maybe constructively or deconstructively interacts with those with that process.
Yeah, that does sound really interesting, actually. Is your work on that published, or?
Well, it's not my work. There's
okay,
just work that I find very interesting, but there's some work by Joris Vos, who did that he tried implementing a bunch of this in his PhD a couple of years ago. And then I think Glenn Michael Oman has been doing a bit of that in post-AGB stars as well.
Okay. Yeah, no, that all sounds really, really interesting. Yeah, I'd love to take a look at that.
Thank you again.
Yeah, thank you. Yeah.
Okay, is there any other question? If not, then I would like to thank JJ again. Thank you very much for your very, very interesting talk. And I like to give the word again to Simon.